Hello, thank you for joining us today. We're really excited to have a stimulating presentation I think you're really going to enjoy by Dr. Robert Borden. He's going to be talking about a new Wikipedia-type site that we have available called Remediapedia. And then the second part of his presentation, he's going to be giving us some examples of lessons learned from EVO injections. I'm really excited to hear that. So Dr. Borden really needs no introduction, but for those of you that haven't worked with him, Dr. Borden serves as the principal engineer with Solutions IES, which is a woman-owned environmental engineering firm that's located in Raleigh, North Carolina. Bob is also a professor of civil, construction, and environmental engineering at North Carolina State University, where he teaches and conducts research on natural and enhanced remediation of hazardous materials in the subsurface. And he's done a lot of work with laboratory studies, field work, and done some really excellent work in mathematical model development. Dr. Borden received his bachelor's and master's in civil and environmental engineering from the University of Virginia and his PhD in environmental engineering from Rice. Bob is the author of over 100 publications and has been the principal investigator on more than 30 different projects. Now, as many of you who have attended our webinars before know, the webinar today is being recorded and it'll be available on the resource section of the Microbial Insights website within the next week. We'll also send out an email to all attendees with a link as soon as that's available. At the end of the webinar, there's going to be a question and answer period. So please go ahead and type all your questions into the GoToWebinar software, and Dr. Borden will answer them for us at the end of the presentation. So without any further delay, I'll go ahead and turn it over to you, Dr. Borden.
Thanks, Dora. As hopefully you all see up on the screen, and if you don't, somebody send me a message, but you should be seeing this slide that says Remediapedia 21st Century Tech Transfer and How to Improve Bioremediation Performance. And with that, I'll get going. Okay. How come I'm not advancing? Okay, sorry. I'm still learning the tools here. There. Okay, so you should now all see a slide showing, it says at the top, www Environmental Restoration Wiki. And what we've gotten funding from EFCCP to try to develop this tech transfer tool. A lot of it's focused on...
Dr. Borden, I think we're still seeing the other how to improve bioremediation slide.
Thank you.
There we go. We got it.
Okay.
That works.
So anyway, so there you see, thank you for interrupting me. At the title at the top, Environmental Restoration Wiki, is the actual, I guess I'm going to say, proper title for the website. But I hate typing that long thing, so we actually have come up with a couple alternative names. And if you were to type in remediapedia.org or erwiki.net or erwiki.org, all of those will link you to the website. You know, it'll just pass through automatically. And I tend to type erwiki.net just because it takes less typing. What you're seeing there is the website. Actually, let me stop for a second. And now, Dora, do you see the actual website?
Yes, we do.
Okay. And so now I'm going to just cruise through the website, show you some different things. You know, this is, I have to warn you, this is still a little bit work in progress. This is sort of our big picture table of contents. We hope, currently, we hope to have about 60 to 70 to maybe even 80 articles up by next spring. As of now, we've got about 42 articles up. And as you see when you go to it, so okay, I'm going to click on natural attenuation here. And hopefully you now just saw the natural attenuation screen. And it's, you know, these sort of short little summaries articles. This one was written by Dr. John Wilson, and it provides some of the basic background on natural attenuation, as well as for those of you, we have, you get down to the bottom, and we've got a pretty good reference list on most of these And the thing what we really try to do is whenever possible, the links are live. So if you go to the natural attenuation section and you want to see the EPA policy on natural attenuation, all you have to do is click here and bring you to that live article. So going back to that website, and let me go backwards here. We're also working to provide some just sort of, not necessarily cutting edge stuff, but useful references. So for example, we've got articles on different contaminants, and I don't know about you, but I'm perpetually trying to look up, what's the molecular weight or what's the solubility of this for that compound. So we've tried to include some decent tables in here for just reference. I actually keep this one linked on my website all the time just because I'm always trying to remember molecular weights. And let's see. I think that's probably it, that all I was going to talk about. I hope you'll go to it and look at it. If you want to get updates, you can click here on Contact Us, basically get on the mailing list, and then once a month you'll get sort of a list of the new articles that have come out. With that, I'm actually going to go back to the presentation. And now you should be seeing a list of the Remediapedia team. What we've got listed up there are all the different technical experts that are writing articles. I think you can see we've got a very impressive list of authors, and hopefully we'll be able to keep this growing for some time. Okay, with that, I'm going to move on and actually talk about bioremediation. So what I'm going to be talking about today is actually summary, sort of some of the major conclusions of two different projects, which were, well, we've completed the sort of project ER 231, numerical modeling of post-remediation impacts, and we're in the middle of ER 201581, where we're actually going out and we're doing fairly detailed performance evaluations of two former EVO projects. What I'd like to do start off with is talking mostly about the first project. But before I get to that, I wanted to sort of review a little bit. GSI, Travis McGuire, has done some really, I think, very valuable things where they've gone out and they've looked at a series of former projects where people have applied different remediation technologies and try to actually look at what kind of treatment are they really getting. And I'm sure many of you see these sort of slides. This is, they published a paper, I don't know how many years ago, but this is an updated version where they've expanded their database. And you can see here, they like to talk about ohm reduction. An ohm is a 1 log unit reduction in concentration. And what they've got shown here is the geometric mean removal for the site. And you can see for bioremediation, typically they're getting, the median is about 1.1 log unit reduction in parent compound concentration. Obviously, some sites are better, some sites are worse. Thermal treatment, a little bit slightly better than that. You can clearly see some sites do very well, some not so well. What I really like to look at, though, is not just the geometric means, but actually some of the data for individual wells. So here's the graph on the left is really representing that same data all over again. This is just for bioremediation, and what you see on the left is the average site concentration after, or actually the geometric mean site concentration after bioremediation, and the value on the x-axis is the average geometric mean concentration before bioremediation. The green dots are all the bio projects, and you can see that there's a fair number here where they've gotten 1 log unit reduction, some even 2, and actually a fair number here where you've got the geometric mean down here, contaminant concentration, at least paired compound, essentially at detection limit. So, really some sites are doing very well. One of my concerns about this is, though, that this is the average for the site. And at least in my opinion, well, it just seems professionally in the project I work on that, we've got 10, 15 wells at the site, and I've got 19 wells that are doing great, and I got one well that just, it doesn't behave like the others. It just doesn't get as clean as quickly or as fast, or there's problems with it. And we end up spending a disproportionate amount of our effort and funds trying to clean up those 1 or 2 problem wells compared to the sort of the other 15 or 20 that are doing well. And that's actually what the graph on the right shows. This is not necessarily, this is not the average. This is looking essentially at the worst well on the site. And so it compares the average concentration or the maximum concentration before treatment to the maximum concentration after treatment. And see there, you can see there's a lot more of these points clustered up close to the 1-to-1 line. If you're on the 1-to-1 line, it says there's essentially 0 treatment. And even then, there's far fewer down here at the detection limit, and most of them are less than 1 log unit. So I think that just simply reinforces that statement that, we usually do a good job on most of the wells, but there's always a few outliers. And so I got this data from Travis, and I replotted it, and that's actually looking at, this is the geometric mean concentration after treatment. This is the this is the maximum concentration after treatment versus the geometric mean. Obviously, the max is always going to be greater than the mean, so everything's above the 1-to-1 line. But you can clearly see here, even though at some of these sites the geometric mean is essentially the detection limit, or 10 micrograms per liter, we can have maximum concentrations of 1 milligram per liter, and even some of these at 10 or 100 milligrams per liter. And again, I don't know about you, but in my experience, even if I'm doing great and the average concentration on the site is very low, if I've got wells of 10 or 100 milligrams per liter, the regulators are probably not going to let us close that site. And that's really just my take home from this data. As I indicated, we have this other project which is funded by CERTA. We went out, we collected data from 37 ERD sites. At these sites, there were 186 injection wells. And rather than just looking at sort of this gross removal, what we wanted to do is not just look at loss of parent compounds, but all the individual daughter products. So the data you're seeing on the screen here this is just one well. I don't know if it's representative. It's probably prettier than most of the wells, but you can see in this well, very good removal of PCE. Started at about 100 micromolar, declined by, let's see, 1, 2, 3, 4 log unit. Maybe that's 5 log unit. Large reductions in PCE, similarly large reductions in TCE. Nice first order decay rates where when we plot it on a log scale, we get a straight line. Not surprisingly, we see some production when PC and TC are going down. We see some production of cis, and then eventually cis goes down. But unhappily, initially not much monochloride, and then monochloride increases, and it really, has sort of flattened out there. So I guess the question I have in looking at this is, did we get really good treatment or really bad treatment? or somewhere in between. I mean, we've got great removal for PCE, the parent compound, but when you look at the daughter products, I'm not sure I would call that great. And it's sort of a question is, how well are we doing? Well, we came up with this integrated parameter that we call sum of organic chlorine. And so what we'll do is we'll convert the molar PCE to molar concentration, TC to molar concentration, DC to molar concentration, and vinyl chloride. And then sum of organic chlorine would be essentially the moles of chlorine bond to an organic molecule. So there's 4 atoms of chlorine in PCE, so 4 times the molar concentration, plus 3 times TCE, plus 2 times DCE, plus vinyl chloride would be total organic chlorine. And that's what that data looks like for at least this well. And so what you can see here is that, well, for PCE, we got over a 4 log unit removal, which was great. But when you actually look at organic chlorine, total organic chlorine, really not much change. Then we start to go down, and it sort of levels out. So we probably got maybe a log unit reduction in organic chlorine, and it's really plateaued here. So we're no longer getting removal because of that vinyl chloride stall, at least in this well. To get a better understanding of that, we do trend analysis where we fit a first order decay line to that, and we try to estimate the rate of removal for organic chlorine as well as all the individual constituents. Here are some of the results from our data mining project from, this is 47 ERD sites, for the other one went 37. I don't remember it. You can see here, not surprisingly, I think consistent with what the GSI study showed, typically about a log unit removal for PCE and TCE for the median. Some are higher, some are lower. Typically lower removals for cis DCE and vinyl chloride. And in fact, here, C final divided by C initial, if it's 1, that means there's no change. So you can actually see quite a few sites where the vinyl chloride concentration at the end of the project, or at least the end of the mining data we were able to obtain, is greater than the initial concentration. Well, when TC goes down but vinyl chloride goes up, I don't know, what does that mean? Are you making progress or not? We like to use this integrated factor sum of organic chlorine, and you can see for sort of the median site, maybe a factor of 5 or 6 reduction. Some much better, but some not as good. And now this is actually, I said the word site, this is well by well. Again, I'm focusing on individual wells, primarily because this idea that, even if you did really well on 15 wells, if you got a couple outliers, you're not going to get the closest site. We took that data and we tried to do some statistics on it, figure out, where are we getting statistically significant decreases. And you can see here, this is just, we used sort of, and some of you may have used a man-Kendall analysis where you can say, is it decreasing or not? We did that same sort of thing here, where if the concentration is declining and at a rate that the slope is great, we have a 95% confidence, then we would call that definitely decreasing, shown by the blue. The green is probably decreasing. White is stable. Red is actually increasing. And so clearly you can see there's a majority of the wells treated. Now this is only injection zone. We've got decreasing trends in TCE and PCE and TCE. But as for vinyl chloride, the fraction that's decreasing is significantly smaller, and we've got a significant fraction that's increasing. So again, summing that up, you can look at total organic chlorine, and to us, this provides sort of a better measure a sort of overall how much progress you're making. We also look at degradation rates. Here you can see typical common degradation. Now, these are we've only extracted here the rates that are statistically significant. So I'm only showing results here for the blue, light blue region. If they were increasing or stable, those values are not plotted in this figure. But for those wells that are decreasing, we've got typically higher rates for PCE and TCE removal. Again, no big surprise, with a little lower rates for DC and vinyl chloride. The overall integrated TOC rate, or some organic chlorine rate, is a little bit lower. But again, about a little bit over 1 per year. So maybe you'd expect a 50% decline in sort of median some organic chlorine for those wells. We also look at not only how long, what the rate is during the active degradation period, but how long that period occurs. So what we're seeing is when we're getting good degradation, the degradation seems to last, well, okay, for PC and TCE, maybe the median is a year or two, with a maximum of maybe 3 years, well, for 75%, a maximum of 3 years. But when you look at some chlorine, it takes a little bit longer. So we're getting really, I think that's consistent. You know, people, a lot of people use ISCO when they want things to happen quickly. This is just supporting that idea that when you look at these wells, when you're getting good degradation, it's still probably going to take 2 or 3 years or so before you get the removal, the sort of maximum removals you're going to get. And then you can multiply this K times this degradation duration to get actually the orders of magnitude removal. And again, this is relatively consistent with the others. You always get a little better removal on PC and TC, and a little less on cis and vinyl chloride, with the integrated values sort of halfway in between. We tried to look at how you can improve this performance. One of the factors we looked at was bioaugmentation. One of the things we definitely saw was that when you bioaugment, you often get, at least in the data we have in our data set, more frequent PC and TC degradation. Actually, you know, we got more frequent production of vinyl chloride where the concentrations went up. I'm not saying absolutely not that bioaugmentation is causing that. What it just says is that there are other things going on. We bioaugment a lot, almost all the time. I do think it has a benefit, but clearly it's not a cure-all. Even at these sites that were bioaugmented, we see a significant fraction of the wells where the concentrations of vinyl chloride were increasing by 2, 3, 4 years out. So it's not a cure-all. Unfortunately, there's wells out there that don't behave the way we want to. And that's really the focus of this next project. So in summary, bioaugmentation is not a cure-all. We often see these, a certain fraction of the wells that are troublesome. And what we really want to focus on is why. As I indicated, we have a second project funded by EFTCP, and what they've allowed us to do is go out to a couple of field sites that were treated with EVO and try to figure out why they're not working as well as maybe we would hope. Okay, the true confessions, I was actively involved when these were done. The first injections of these sites were in 2006, 10 years ago. This was fairly early in the use of EVO for in situ bioremediation, and we might not have done. Certainly, I think today we would do things differently than we did back then. But we feel it's useful to go back and sometimes and look at what you did before and try to learn from it. At this site, what the injection approach was, we've got a treatment area that's, I'm going to really say 45 feet in diameter that we're focusing on. They put in a center extraction well surrounded by 6 injection wells. You can see this particle lines here. That's the sort of simulated path that the injected reagent would follow, flowing towards the middle. This site was actually, we were trying to treat an interval from about 15 feet to 40 feet. And so what they did is they used 2 10-foot screens. The upper screen went from 15 to 25 feet. The lower screen went from 30 to 40 feet. They injected about 7,500 pounds of EOS and 78,000 gallons of water with the EOS to distribute it. It was working, but it seemed the remediation was slowing down after about 5 years. So in 2012, they went back and they re-injected the same wells, but they used a significantly smaller amount of EOS. At that time, they also added a little bit of buffer, but I think you'll see the buffer addition may not have been enough as much as we should have added. Here's sort of the layout. The light blue are injection wells. The center EWO1 and EWO2 are the extraction wells. During our investigation, we went out and we put in some additional HPT points to get in measure the hydraulic conductivity and the contaminant distribution. And we've got some shown by the dark blue monitor wells and black monitor wells scattered in both the A or the B and the C, the B and the C zones. Here's a profile through the site. The zigzag lines you're seeing here are hydraulic conductivity profiles. So you can see we've got basically fine sand throughout the vertical profile down to about 45 feet where we hit a clay layer. The 2 injection zones, the B zone here was where we've got the upper 10-foot screen, and then the C zone, the lower 10-foot screen, and a 5-foot interval in between. At other areas of the site, this interval between the B and C was, there was a lower permeability silty sand there. At this specific location, we didn't find that silty sand. It pretty good permeability all the way through. The upper zone, hydraulic conductivity is a little bit higher at 3 to 6 feet per day. Actually, I'm sorry, it's a little bit lower at 3 to 6 feet per day versus deeper at 6 to 8, but really not a giant difference. I think the bigger difference is the pH in the upper zone was maybe 5.6 to 6.4, whereas the lower zone was a little bit lower, lower pH. We also have sort of an odd situation where there's, in part of the area, there's an upward hydraulic gradient from the B zone to a drainage ditch off on the left, versus deeper down, there's actually a downward gradient from the C zone to deeper in the formation. So to start off, again, here's our center extraction well. We've got an injection well here. I'm going to look at this one monitoring well here. So we're almost in a perfect straight line between this injection well and this extraction well. So you'd expect that well to do pretty well. Yeah, anyway. And in fact, it did. What I'm showing here is chlorinated ephines on the top graph, then sum of organic chlorine, chlorine number, and pH. You can see in 2006, they injected EOS, got a very nice removal in TCE, went down, what's that, 1, 2, 3, almost 4 log units. Got some production of DC and vinyl chloride, but you know, overall it's doing pretty good. And then re-injected, and here in uh, I guess about 2015 is that most recent data. That you can see the dark black is ethene. We've got ethene concentrations of over 100 micrograms per liter. So sounds like we're doing pretty good. When you look at degradation rates for some of organic chlorine, again, we've got a degradation of 3 per year. That's actually sort of at the upper end of the range of degradation rates that I showed you in those earlier figures. And I think that reflects that this well is doing what it's supposed to. In addition to looking at some of organic chlorine, we also calculate chlorine number, which is sort of a weighted average. If you take some of organic chlorine divided by sum of ethenes, that will give you chlorine number. So for example, we start out here early on, it's virtually all TCE. Well, TCE's got 3 chlorines per molecule. And so it's got the aquifer's got an average chlorine number of 3. As we convert from TCE to a mixture of DCE, vinyl chloride, and ethene, it drops down to about 1. There's some cis and there's some ethene, but it's sort of average. It averages out as equivalent to vinyl chloride. And now down here, we've got chlorine numbers almost close to 0. And what that says is stoichiometrically, we have significantly more ethene than we do vinyl chloride and very little cis at this point, or TCE. So we're getting almost all the way there and feel like this well is doing pretty well. Initially, the pH was about 7. Shortly after dechlorination started, there's a pretty rapid drop. pH dropped down to below 6 at about 5.5. And we think that's probably part of the reason why it seemed to sort of stall here a little bit. Even though we're making a decent amount of ethane, we still got it quite a bit. When we went back and added some buffer, didn't rise up real high, but after GL12, we got up about 6. Once the pH got at about 6, that allowed the dechlorination to go further, and we feel like we got real good removal here. And this story, it's not identical for all the other wells in the B zone, but it's actually, fairly similar. Early on, again, these are some of the other wells. So we've got wells 55B, 56B. Here, chlorine number, some of organic chlorine declines, chlorine number declines. It stabilizes out about 1 or so. And again, these other wells here, pH drops below 6. We get a problem when we bump the pH back up. Degradation continues. So wells 55B and 56B are doing pretty well. Versus you look at some of these other wells, not quite as good. Here, again, some of chlorine declines, but then it pops back up, like we're not getting as good as removal as we want. Again, the chlorine number comes down, but at least, say here at 57B, it seems to stagnate, and we stall it at cis here with a chlorine number of 2. And it's not until we add buffer that it goes further down. And you can see in some of these wells, now we've got pHs, this one, probably worst well here, 57B, it stalled at a pH at a chlorine number of 2. Well, that's because the pH was about 5. And it wasn't until we got the pH up higher that we went down. So, overall, we feel like this is, at least the second edition was a success. We added enough buffer, maybe not to get the pH to optimum level, but at least up to around 6. And once it goes up about 6, we're continuing to get better removal. So it's taken some years, but we're making pretty good progress. Now, you go to C-zone wells. Not so good. If we look at these wells here, we start out here at pretty high concentration. chlorine numbers initially declined, but you can see here, I mean, really not that much. And even after we re-inject in 2015, it only goes down by about a log unit. We were hoping for more than that. Here, some organic chlorine again here, I don't know, maybe it goes down by a factor of 10, but probably not even that, and we're kind of stalled here. When we re-inject in 2015, the chlorine number comes down to about 2, and then really stops, get no further degradation. Well, if you look at the pH values, here we're below 5.5 pretty much the whole time. We re-injected in 2012. We get a jump in pH almost up to 7 in a few wells, but then it very quickly drops back down. Clearly, we didn't have enough buffer here. And again, you can see the same thing up here. We get a few temporary spikes above 6, but for a large measure, our pH values are below 5.5. I'll talk that about in a little bit more, but clearly in the C zone, we didn't have enough buffer. The pH started out a little bit lower. It appears to have a greater buffering capacity that I'll show you, and we're just not adding enough. One thing I'd like to go back, and one of the things that surprised me about this is that, we have some organic chlorine go down, and then it goes back up. Well, we thought we were treating the source area, so it's clearly we're getting more material coming in from somewhere. Well, we wanted to go back and try to figure that out. So what we did is we looked here. I'm going to look here at this specific well, and you can see here I put an HPT profile right next to it. Actually, it's a MIP HPT profile next to it. And when we do that, you can see, well, let me actually go back. This is HPT 1, 2, 3, 4, and 5. And what you see here in the center, the one I have circled, is really the only one where we get a good hit on the XSD detector. 1 is, for all intents and purposes, clean. 4 and 3 are really pretty clean. We do get a little bit of hit, but now this is down in the clay, well below our injection interval. The only place where we really have a significant level of contamination is here in this SA1702, which is our HPT 2 point. So we've got a big hit here. Now, one thing you should point out here is the MIP is saying we've got a peak here in the middle of our zone C at about 30 to 40 feet, I don't know, 32, 35 feet below grade. We wanted to go investigate that a little bit more, so we went out and took continuous cores from right adjoining that interval. And when we took continuous cores, we found that actually the contamination wasn't at like 32 feet. It was really a little bit higher up. And I think the MIP was sort of giving us a misreading just because the carryover in the MIP, it took a little while to get the reading. And we've got this zone here, mostly from 25 to 30 feet, where we've still got very high concentrations of TCE. Now, they're soil cores, so these are really the measured concentrations in micrograms per gram. But I have a hard time thinking those numbers, so I try to convert it to sort of an equivalent aqueous concentration. These are the concentrations that if 100% of the TC were dissolved in the pore water, this is what you get. Now, 100% isn't dissolved. Probably the soil's got a retardation factor of 4 or 5, so maybe the actual measured concentration in the pore water is a fifth of that. But we've got a decent amount of TCE here and a little bit of cis. So clearly there's this zone that's untreated. Well, number one, remember our B injection interval goes from 15 to 25 feet. And our C injection interval goes from 30 to 40 feet. So we've got this residual sort of halfway in between our injection zones. We went back and we tried to sort of figure out how that worked. I had assumed that, well, if we're injecting from 15 to 25 feet and, you know, you get some sort of mixing or dispersion or something, and you'd think you'd get a little treatment above and below. Well, what we try to do is figure out is, you know, is that actually true? So we simulated the injection process with ModFlow and MT3D. Now, this is a non-reactive simulation. We're doing some currently ones where we're actually looking at EVO transport, but if a non-reactive tracer isn't going to get there, then the EVO clearly is not going to get there. And so this is our injection well pattern. This is the sort of simulated distribution of a non-reactive tracer in the B zone. And you can see here that well that I was pointing out before, this well here, MW53 with 4 different screens here, but it's MW53 right here, is this well right here. And by us just injecting here and extracting here, it's sort of pulling the EVO straight over, and we have these sort of holes in the injection area where we're really not getting, you know, at least the model says we're going to get very poor distribution in the EVO in all these white areas, and we're really only going to treat the blue areas. Now this is in the B zone. In that gap at 28 feet, that gap between the B zone and the C zone, the distribution is much poorer. It's saying we would expect this area to be basically untreated. And now we go down to the C zone, and more of it's treated, but we still have some gaps. This well 53 is untreated, and actually you can't see it, but 55B, that was one of the other ones that we had problems with. So my take home from this is that, well, we left some holes. We just left some areas that didn't get treated. They didn't get contacted with EVO, and then they didn't get contacted with buffer. And, well, if you don't deliver the substrate to the point, you don't get treatment. And even though you go back, and based on this profile, over here is clean, and the monitor well here shows that this is almost completely treated. This is almost completely treated. This is almost completely treated. We've got great treatment here. We've still got little blotches or hot spots inside this treatment area that we missed. And so the net result is we have, you know, 8 or 10 good wells and 2 or 3 bad wells. So pockets of VOCs that we just didn't treat, didn't have enough buffer to treat the low pH in the C zone. And so we're now in the process of developing one method to determine how much buffer to add for this specific site, and develop some guidance and tools to sort of figure out how to keep this from happening again. I don't know how long I've been talking, 37 minutes. I still have a few more slides. Dora, would it be a good time to stop and take a few questions, or should I keep going and try to do a few more slides?
You can do a few more slides, and then if we go over a little bit, we'll have it recorded. If anyone needs to leave, they can come back later and catch the end of the session. So, yeah, let's go ahead and finish.
Okay. I think most of you know why pH is important, but I'll cover that a little bit and then do some, cover some material about how to estimate how much base you need to add. This is some graphs that I borrowed from a student, well, not a former student of David Friedman's, Ashley Eady. She developed a bioaugmentation culture from the Savannah River site and then tested degradation kinetics at a number of different pHs. What you can see here, TCE conversion to DCE, excellent removal rates at pH 7, both buffered and unbuffered, at pH 6.5, not bad at all. This blue line here even is at pH 5.5. At pH 5.5, degradation was clearly slower, but eventually, it caught up. And then, even here at, let's see, I guess that's pH 8 is the one that they never got removal on. 8.5, I'm sorry. But at 5.5, even though it was slower, they eventually got degradation of TCE to DCE. However, when you look at removal, now this is a separate bottle where they just added vinyl chloride. Again, pH 7, very good removal. At pH 6.5, a little bit slower, but again, eventually very good removal. At pH 6, well, quite a bit slower. They are getting some vinyl chloride to ethane conversion, and at 5.5, just nothing. And I think that's what we saw. Clearly, somewhere, 5.5. If you're below 5.5, you got a real problem. And even at 6, it's certainly suboptimal for conversion of vinyl chloride to ethene. One thing I like to emphasize to people is certainly low pH is bad, but pH really does not tell you how much base to add. This is just a sort of simple example, but we've got, this is an example of taking water. One solution contains half normal HCl, and it's got initial pH of a little bit over 3. And a second solution has 1 normal acetic acid. As you add sodium hydroxide to that to raise the pH, you can see here it takes you, even though the initial pH of the HCl was lower, it takes you twice as much acid or base to raise the pH up to 7. And that's the normality. So if you just tested these water samples here, you'd see this initial pH was lower. You'd think it takes more base here. Well, no, it doesn't. You need to look at the acidity, not just the pH, and acidity is different. And I'll try to explain how to do that now. Okay. Now, where does this acid come from? As you all know, you dechlorinate PCE to ethene, you remove some chlorines, and they get released to solution. Well, in addition to releasing chlorines, you also release protons, and essentially when you dechlorinate 1 mole of PCE, you produce 1 mole of ethene and 4 moles of hydrochloric acid. That's definitely going to drop the pH. If you add carbon, now I'm talking about soybean oil here, but if you add lactate or butyrate or molasses or any other carbon source, basically that carbon is going to ferment. It's going to release hydrogen and carbon dioxide. Carbon dioxide plus water makes carbonic acid. So I need to stop for a second and sort of do an overview of the carbonate system. So if you add carbon dioxide to water, you get H2CO3. I'm going to call that carbonic acid. If you're at pH 8, all that carbonic acid is going to disassociate to a carbonate and an H+. So for every 1 mole of carbonic acid, you're going to release 1 mole at pH 8.3, 1 mole of bicarbonate, and 1 mole of protons, H+. If you were to add bicarbonate, sodium bicarbonate at pH 8.3, 1 mole of sodium bicarbonate goes to 1 mole of bicarbonate, and you actually don't produce or consume any protons. If you add carbonate, CO3, it'll consume 1 mole of protons, making bicarbonate at 8.3. Well, the amount of protons added or removed varies as a function of pH. So I came up with this little, simplified version. If you've had aquatic chemistry, you can figure this out a different way, but I find this convenient. So I'll look here and say, if I'm at pH 4, 1 mole of CO2 plus 1 mole of water makes alpha moles of H2CO3 and 1 minus alpha moles of HCO3. So at pH 8, alpha is what, 0.05. So at pH 8, for every mole of CO2, you produce 0.05 moles of carbonic acid and 0.95 moles of HCO3. At pH 7, you produce 0.8 moles of carbonic acid and 0.2 moles of, 0.2 moles of this and 0.8 moles of that. But that also works with adding bicarbonate. So if you add bicarbonate and HCO3, and you want to get the pH to 7, alpha here is about 0.1 at pH 7. So every mole of bicarbonate you add, it consumes 0.1 moles of acidity, produces 0.9 moles of HCO3, and 0.1 moles of carbonic acid. So at pH 7, 1 mole of bicarbonate only consumes 0.1 moles of acidity. It's not a very efficient buffer. Carbonate, so sodium carbonate, not sodium bicarbonate, would consume 1 plus alpha moles of acid. Much more effective, much better at raising the pH. That's why sometimes when people add sodium bicarbonate, they don't get the pH rise that they were hoping for. The other thing you have to understand is titrations you do in a lab don't necessarily match what happens in the field, in an aquifer. In the lab, if I add sodium bicarbonate to an acid, the bicarbonate dissociates, releasing a sodium and an HCO3, and the acidity combines with that. It makes carbon dioxide, and this carbon dioxide degasses, it fizzes. And so this reaction essentially goes to completion, where sodium bicarbonate plus acid produces a sodium, a water, and CO2, but the CO2 fizzes out. You're basically fizzing off the acid. In a closed system below the water table, where it can't degas, you get this equilibrium relationship where for every mole of sodium bicarbonate, you only consume alpha moles of H+. And I know that's kind of confusing, but it's the problem with it not degassing. If it doesn't degas, you don't get the same effect. Okay, where does a lot of acidity come from? I live in Raleigh, North Carolina here, in that dark brown area here. The pH of the soils in this area often they start out less than 5. Now, the project I just talked to you about was in down near Jacksonville, Florida. Here, the ambient pH, again, is fairly dark red, so the actual natural pH of the soil was already about 5, 5.5. If you're in the western United States, in these blue areas, the ambient pH of the soils are often quite a bit higher. They have a lot less rainfall, and so you're not working against an initially low pH. So one of the other things that buffer pH in an aquifer, a big effect is proton exchange. If you've got clays in the soil, they're going to have cation exchange sites on them. Those cation exchanges sites can be filled with base cations like sodium or calcium, or they can be filled with protons, H pluses. So if you have a naturally low, when you add an acid to the aquifer, if there's a sodium absorbed to that cation exchange site, you'll bump off the sodium and the proton will absorb. That'll slow the decline in pH. So for example, if you add CO2 or carbonic acid, the carbonic acid will bump off the sodium, the proton will absorb, and you release a bicarbonate and a sodium. That will limit the pH decline. But the flip side of it is, if you then want to raise the pH, if you add sodium hydroxide or another base, as you add the sodium hydroxide, that proton will be released. The sodium you add will absorb, and it'll limit the pH increase. Bottom line, aquifers have a really, really strong buffering capacity, particularly if you've got a lot of silts and clays. They're often very, very well buffered. It's hard to reduce the pH, but it's hard to increase the pH. Well, how do you know? What we do is we collect soil samples. So from that site I showed you before, the purple numbers here are from the B zone. The black numbers are from the C zone. Well, actually, the black numbers are below the C zone. The red numbers are from the C zone. And what you can see here is the initial pH of these materials started out at, we collected the soil, the initial pH was anywhere from like 4 to 5, and then we titrated it. So we added sodium hydroxide, and we report the results in moles of equivalents of sodium hydroxide per kilogram of soil. In the B zone here, this purple line, when we added 0.05 hydroxides per kilogram, the pH went from initial about 5 up to a little bit over 7. Now, you don't want to go up here to 8 or 9, but we do want to get to 7. Versus if you look at the B zone, or I'm sorry, the C zone, the red lines here, to get to a pH of 7, we had to add more. These red lines are over here. So for the B zone, we need to add about 0.0057 hydroxides per kilogram, versus in the C zone, we have to add about 0.0084 hydroxides per kilogram. So if we want to treat basically a 50-foot diameter circle, if our target pH is 7, our treatment target duration is 5 years. Well, I can figure out how much soil is in that zone. It's about 2.5 times 10 to the 6 kilograms of soil. I can also figure out how much groundwater flows through. And so I can add up and I can figure out how much base I'm going to have to add to each zone to get the pH where I want it. This upper line is the initial soil acidity. That's the titration I just showed you. There's also CO2 produced from the vegetable oil I'm going to add. There's the TC I'm going to degrade. There's the natural groundwater acidity. You can see here the groundwater acidity is much lower than the soil acidity. To a large extent, groundwater acidity is almost round off error compared to the amount of acidity from the soil and the CO2 I'm going to produce and the TCE I'm going to degrade. There's also actually a natural buffering from the electron acceptors that get consumed. When you reduce nitric acid, NO3, you're really sort of reducing nitric acid. If you reduce sulfate, you're reducing sulfuric acid, and that's actually going to act to raise the pH and sort of counteract some of the effects of the CO2 and the soil acidity. But the net effect is to degrade, to raise the pH to the target level. I should have added 9,000 equivalents of base to the B zone and about 12,000 to the C zone. Well, as you're going to see, we didn't do that. You can look at different bases. These are sort of the common ones: magnesium hydroxide and milk of magnesia, calcium hydroxide or hydrated lime, caustic soda, soda ash. That's the sodium carbonate versus baking soda, which is sodium bicarbonate. You can look at the moles of protons or OHs released or protons consumed per mole of these materials. And you can also look at it in kilograms here. And you can see things like hydroxides, magnesium hydroxide, calcium hydroxide, sodium hydroxide release a lot of OHs per kilogram. Compared to like baking soda, which will only release a really pretty small amount. The downside of it is these generate high pHs. We don't want too low a pH, but we certainly don't want too high a pH either, because that'll fry your aquifer. Sodium hydroxide is easy to add. It's very, very soluble, but if you add all that sodium hydroxide, the pH around the injection well is going to be 14, and you're just going to kill all the bugs. Milk of magnesia doesn't generate nearly as high a pH, so that's less of a concern, but it's essentially insoluble. So I know you don't like this answer, but there's really no good answer. They all have their limitations. Okay, so we went through and did a calculation trying to figure out, okay, how much of these different bases I would need to add for both the B zone and the C zone. Taking the injection concentration, aqueous ratio of aqueous solubility. Sodium hydroxide is really soluble, so we're going to be injecting at 4% of the aqueous solubility. Sodium bicarbonate, we have to add a lot more, so we're going to be injecting at 60% aqueous solubility. Magnesium hydroxide to add it is essentially insoluble, so we're going to be 9,000 times the aqueous solubility. So we inject it, very little is going to dissolve. It's going to be actually as colloidal particles. Injection solution pHs. If you inject sodium hydroxide, it's going to be pH 14, bicarbonate's 8.3, so magnesium hydroxide will be 9.5. You can see here some quite significant amounts. These are the base required. If you remember before, I said we injected, at least in the second injection, we injected a total of a little bit over 2,000 pounds of EVO. If you look at the pounds of base we're talking to add, 9,000, 12,000 pounds. You're talking about, if you tried to do the sodium bicarbonate, you might have to add 10 times as much sodium bicarbonate as the EVO. You don't have to add nearly as much sodium hydroxide, but you fry your aquifer. Magnesium hydroxide, significantly lower amounts, but still quite significant. If you look down here, the amount we actually added was 49 pounds of magnesium hydroxide compared to the amount we needed. So clearly, we significantly underdosed this aquifer. And sorry, didn't know it, but that's what we did. So, summary. You really, pH 5.5, as far as I'm concerned, is the absolute minimum for good dechlorination, and really you want above 6. Now, in my calculations, I said I wanted to get up to 7. Our design protocol is we like to get the pH up to 7 initially, so that as the process goes along, if we produce a little bit of acid, the pH can drop down to 6.5, and we're still okay. If you only initially get it up to 6, then when you produce some acid, now you're dropping down to 6.5, and you're not as good. Key thing is really large amounts of some of these alkalis are needed, particularly if you're going to do sodium bicarbonate. You're talking about a lot of sodium bicarbonate to get it up to the target pH. Soda ash works better, but again, you can get high pH issues with soda ash. The other issue I think people need to be aware of is, if you go back here, we looked at the amount of sodium you're adding. If you add enough sodium bicarbonate to raise the pH, you're going to get sodium concentration in the aquifer that are well above drinking water standards. And while you may degrade all the TCE, you're going to have a total dissolved solids issue. So thank you very much, and I think that's it.
All right, thank you very much, Dr. Borden. We do have a few questions that are coming in right now, and it looks like the questions in the beginning related to your discussion on the organic chloride and using that along with your sum of the mole fractions. And I guess there are several questions wanting you to explain that, and one of the concerns is that because chloride can be difficult because it can leave the site at a faster rate than the daughter products. And so, kind of getting your recommendations on the best way to manage that, explain it a little further, and then how do you explain to people that's the best way to handle that if they're not seeing as much chloride as they would expect to be formed?
Understand your question, and absolutely, number one, you may not see the chloride produced, or simply the background chloride may be so high that you actually don't see an increase in chloride. No, I'm not actually advocating measuring chloride. We do typically, but I agree that it usually is not diagnostic. No, what I'm advocating is that you, instead of just looking at PCE removal or TC removal, you can get this sort of integrated parameter where essentially, if you want to think of it, sum of chloride is essentially a weighted average or a weighted sum of the individual constituents. So the way you calculate sum of organic chloride is you take 4 times the mole fraction of this, plus 3 times the mole fraction of this, plus 2 times the molar concentration of this, plus 1 times the molar concentration of methyl chloride, and that gives you the sum of what's still there. Obviously, if these constituents migrate away, then you're going to see them down gradient. But this is just in the injection zone, and this is, so if we remove 1 mole of PCE, but we make 1 mole of vinyl chloride, the total ethenes would stay constant, but organic chloride would decline from 4 times the moles to 1 times the moles, so we get a net removal of 3 moles of organic chloride. Does that make sense?
Yes, it does.
Okay.
Okay, great. Yeah, I think that's very helpful. Okay, the next question is that, sometimes with the remediation goals, it may include reduction of the contaminant mass as well as a reduction in the contaminant toxicity. So if we recognize that there's a more relatively benign state of DCE, do you have insight regarding making DCE stall a remediation objective?
I if you were, okay, true confessions, I have actually, done that at sites where the initial TCE concentration was relatively low. So, for example, if you've got 20 micrograms per liter TCE to start with, and the cleanup standard for DCE is 70, there's no way 20 micrograms per liter of DCE TCE is going to exceed the DC standard. But if we're starting here at 10,000 micrograms per liter of TCE, my experience is it's been very tough to stop at cis and not make any vinyl chloride, even if most of it stops at cis. We always produce enough vinyl chloride to be a problem. So that's, at least at higher initial concentrations, that's not been a successful strategy for us. And I'm not sure how I get a regulator to approve that either, but guess I shouldn't say that on the phone.
Okay, I think a good follow-up question to that is, so once you've generated vinyl chloride and it becomes an issue, do you ever recommend trying an aerobic treatment rather than anaerobic mechanisms?
Then certainly if you had a plume and you had completely removed the TCE in the upgraded area and you had strictly a DCE plume or a vinyl chloride plume, certainly you could put an air spargic wall or something like that further down gradient. That's never happened to us, typically, and so that would be down gradient. Typically, if we still got vinyl chloride, we'll probably still have some detectable, but that would be down gradient. If you're at a source area and you're making, like in examples I showed you here, okay, this well here, the chlorine number in 57B, the chlorine number here is stalled out at 2. So you could go, okay, well, I could stop anaerobic and I could treat this aerobically. Well, no, you really couldn't. This is, the fact that it's stalled here at 2 is twofold. One, the biology stopped because of low pH, but there was this big chunk of TCE out there that I didn't know where it was. I've still got a bunch of TCE here in this aquifer, even though when I look at the monitor well data for well 53, if I look at the monitor well data for well 53 C1, that goes from 30 feet to 35 feet, I've got loads of TCE in this formation. But well 53 C1 has got a chlorine number less than 2. When we sample, I don't have a graph of the actual numbers, but TCE is essentially below detection in this well. Because what's happening is, even though I've got TCE out in the soil, as that TCE dissolves and migrates through the aquifer to my monitor well, it very, very quickly gets degraded to cis. And so my monitor well says I've only got cis in the aquifer, even though I got a bunch of TC in the soil. If I were to stop that process right now and stop converting TCE to cis and try to degrade the cis aerobically, I'd get a giant rebound in TCE there. So my experience is if you're still continuing to have cis present, it means there's some TCE out there that you haven't found and you haven't treated. And I would not recommend converting to aerobic until all the TCE is gone. And it's really hard to find all of it.
That makes sense. Okay, the next question talks about the soil acidity testing that you recommend. Is there a standard method, such as an ASTM method, for that type of testing?
No. There is a method that Microbial Insights will run for you that is very, very similar to this test. Now, Dora, I'll tell you, we're working to sort of upgrade this protocol a little bit, and we'll probably be sending you a slightly modified one in a month or two.
Okay.
But you know, it's really a fairly slight modification. So Microbial Insights will do it for you. It's not a terribly difficult test.
Okay, and are you willing to make the slides available if anyone's interested in having those, Dr. Borden?
Sure. What I should have said too is particularly these earlier slides with the chlorine number, that is all described in a CERTIP report. If you look at the beginning of it, if you search for that project number and you go online, it'll pop up. And actually, let me go back and do my advertisement. So, if you want to go find that article on the sum of organic chlorine, go to the Remediapedia, search for secondary water quality impact of anaerobic bioremediation. Click here and it will lead you to the project site with all of the reports, including protocol for monitoring that. So if you want to copy that report, just go to the Remediapedia and search for it and you'll find it.
That's great. Remediapedia is a very useful tool. Okay, one last question for you, Dr. Borden. If you're talking about moving to more aerobic remediation protocols, what are your thoughts on pH buffers? Is it any different when you're approaching that versus anaerobic remediation?
I don't know. If it's aerobic remediation of petroleum hydrocarbons, the energetics of that process are so wonderful. The bacteria just get so much energy from that. They tend to be less pH sensitive. But anaerobic bioremediation of petroleum hydrocarbons, well, again, the energetics stink, and so they tend to be more pH sensitive. And chlorinated solvents, again, the energetics stink. And even, I don't know of any data on the pH sensitivity, but getting aerobes to degrade vinyl chloride or cis DCE, I mean, there's some that do it, but they don't do it real well. And I would suspect they'd be somewhat pH sensitive.
All right. Well, thank you, Dr. Borden, and thank you for taking the additional time with us today. It's rare to have the opportunity to pick the brain of a scientist like you, so it was exciting to have you on today. And thank you, everyone, for attending our webinar. If you have additional questions or you would like some further information, you can contact us at info@microbe.com, or you can also email Dr. Borden. His email address is rcborden@solutions-ies.com. Feel free to contact either one of us. We'll be happy to answer your questions. And again, the recording of this will be on the website within the next week, so you'll be able to listen to this presentation again. Thank you all, and thank you, Dr. Borden. Have a wonderful day.
Thank you. Bye-bye.
Bye-bye.